Joe?
Okay.
Okay, good afternoon, everybody. I'm trying to do this Zoom conference the first time, big conference with so many people attending. And this is a project that CMSA in Harvard start to work on. Namely, we are talking about history and literature, math science. It's a joint program with the Tsinghua University Math Center in China. In China, we started out last year with Wilbur Schmidt and John Cox. Wilbur talked about Lie theory, history Lie theory, and John Cox talked about number theory. So we felt that it's very interesting and would be very useful for many people in different subjects to learn different aspects of mathematics. And we asked the most prominent people in the field to explain what they know. I actually gave a lecture on Chern, my teacher, about his development, and it is now in our website, which you can take a look. So I felt many people said that they learned a lot by listening to Wilbur Smith, to John Cox, and my talk. And we had Don Rubin gave a talk in statistics. So now this is the first time on Zoom, and I think it's very interesting. And the lectures will be written up, and we will publish those lectures each year. But in any case, the lectures will be in the website of CMSA. So I hope you will enjoy it. And of course, you can give comments later. So here we have Joe Harris, who I knew for more than 40 years ago in Harvard when he was a graduate student. In fact, when I proved the Calabi conjecture in 1976, I came to MIT and ended up to be talking much more in Harvard. And Joe was a graduate student at that time. He was writing his book with Griffiths. And it's a very nice book. And in fact, the book I'm still using at this moment in my class. And so Joe, of course, since graduate school has been doing great, being one of the most prominent algebraic geometer, one of the best leader in the subject, writing many books and make important and extremely influential development in algebraic geometry, in particular in algebraic curves and rationality problems. So today he's going to talk about rationality in algebraic geometry. So Joe.
Okay, well, thank you. And so let me start by saying what I'm going to talk about. Originally, the idea was, as Yao suggested, I talk about the question of rationality in algebraic geometry. And my thesis was going to be that questions of rationality have historically driven the subject of algebraic geometry forward. And I realized as I started to prepare the talk and tried to write down examples of this, that in fact I could be much more specific. It's questions about the rationality of cubic hypersurfaces specifically that has driven algebraic geometry forward. So I'll talk about rationality in general, but it is really striking to me that the key examples in dimensions 1, 2, 3, and 4 are all going to be cubic hypersurfaces. So you can take from that what you will. The one thing I want to say before anything else is that we're going to be working exclusively over the complex numbers. Rationality has always been an issue over non-algebraically closed fields. When you're looking for example, solutions of Diophantine equations, points on algebraic varieties over number fields, for example, then this is one of the key drivers of our interest in rationality of varieties. But I want to just keep things simple and relatively geometric, so I'm going to be working entirely over the complex numbers. And I think any discussion of rationality has to begin with the question, what do we mean when we talk about solving a polynomial equation or a system polynomial equations. Again, just to keep it simple, I just want to think in terms of a single polynomial equation defining a hypersurface in affine or projective space. What does it mean to solve the polynomial equation? Well, if it's a polynomial in one variable, then of course it just means finding the solutions. There's finitely many solutions, and hopefully you can write them all down. In higher dimensions, though, if we have a polynomial in two or more variables, we should say what it means to solve it. And what I propose as the meaning of solving the polynomial equation is to express the general solution of the equation as a rational function or rational functions of a free set of variables. So the idea would be that if we have a polynomial f of x1 up to xn equals 0, we want to find all solutions. Well, we're not going to actually ask for quite that much. Instead, what we want is to express the general solution as a rational function, say, of free variables t1 up to tn minus 1. Okay? And, you know, this, let me just start with one basic example that, wait, I see a question.
Hey, Joe, I'm just going to interrupt you there for a second. Your screen is not pinned, so people cannot see what you're writing. So okay. Would you like me to pin that for you?
Yes, actually, it's according to my machine, it says it's pinned, but why don't I'm gonna. Okay, if you can fix that, that would be great.
Hold on, give me a moment.
Okay, so let me know when to proceed.
All right, you're all set.
Okay, good. Now, I'm afraid that now that you can see this, what I'm writing, you can also see that I have some technical issues on this end. Namely, the sunlight is coming in and there's a shade cast over part of the page, so I will try to avoid that. Okay, so I just to be concrete, I want to do an example. And it's one that you guys have all seen, but it's relevant to what I'm going to say in the case of dimension 1. The standard example here would be to take something like the equation, let's say w squared equals z squared plus 1. So that corresponds to a hyperbola in the plane. And in this case here, I can solve the equation by simply choosing a point. Let's say take the point 0, 1 on the curve, and then if you take a line, any line through that point, let's say we call L lambda, that's going to be the line with slope lambda through the point we picked out, 0, 1, and that will intersect the curve in exactly one other point with a finite number of exceptions. That point will be the point 2 lambda over 1 minus lambda squared plus 1 over 1 minus lambda squared. And there we have a rational parameterization. A general solution of this equation is given parametrically by the pair of functions 2 lambda 1 over 1 minus lambda squared and lambda squared plus 1 over 1 minus lambda squared. So this is an example of what I mean by a solution to the problem. In general, though, it's worth pointing out that you don't necessarily get a one-to-one correspondence between solutions of the polynomial and values of your free variable, in this case lambda. What you get is a parameterization of all solutions in a Zariski open subset, or as the complement of a closed subvariety. Okay. Now, this came up, actually, strangely enough, for the first time in the 19th century. And the situation was, interestingly, not algebraic geometry or even algebra in general, but rather it was calculus. When people first started doing calculus, which was, in the 17th and 18th centuries, they began to apply it to various problems, and they, in particular, they used it to solve a bunch of problems from geometry and physics elsewhere. And they built up a roster of elementary functions whose integrals they could evaluate in terms of other elementary functions. The standard ones, the rational functions, which you do by partial fractions, and trig and inverse trig, exponential and logarithmic functions, the functions you learn how to integrate the first time you take a course in calculus. And this even included some algebraic functions. So these are functions that involve functions defined implicitly by polynomial equations. And so, for example, they did integrals like dz over square root of z squared plus 1. Now, nowadays when you're taught calculus, typically you do this by a trig substitution. More generally, any integral of an algebraic function involving a square root of a quadratic polynomial, you do by trig substitution. But I would propose, and I think this is not completely alien to the spirit of how it was originally done, a more general way of approaching these integrals is to use the fact that this is, not so much the integral of a multi-valued function on the plane, on the z-plane, but rather think of it as a path integral on the zero locus of the polynomial w squared equals z squared plus 1. I could write this as the integral of dz over w on the variety defined by w squared equals z squared plus 1. And then we can use the rational parameterization that we just described on the previous page to convert this to an integral of a rational function of lambda d lambda. And of course, that we know how to do because we've developed the technique of partial fractions. So this is sort of a general way of approaching basic problems in integration that involve the square root of a quadratic polynomial. And it works because that the curve in the plane defined by the square root of that quadratic polynomial is a rational curve. So that's where things stood at the beginning of the 19th century. And then they came across an integral, which they couldn't do. This was the integral. Well, I'm going to write this as a stand-in for integrals of a certain form. I want to take dz over the square root of a cubic polynomial in z. And just to keep it simple, I'm going to take z cubed plus 1 here. Okay? And this is an integral that comes up in the course of trying to calculate the arc length on an ellipse in the plane. And for that reason, these integrals have always been called elliptic integrals. But now, they couldn't do it. Basically, they tried, and I think it was a period of almost half a century from the time they first encountered this integral to the time that they began to get a glimmer of some understanding of why they couldn't integrate it, why this was something that was outside the realm of functions whose integrals they could express in terms of known elementary functions. What eventually transpired was that after a number of decades of movement in this direction, Riemann was finally motivated to look at the zero locus of the corresponding polynomial equation, w squared equals z cubed plus 1. And he proposed to look at it not just over the real numbers, but over the complex numbers. And if you look at the zero locus of that polynomial in C2. So that's paired ZW in C cross C such that W squared equals ZQ plus 1. That's a surface inside C cross C. You can see what it looks like by considering the projection map to the Z-plane, which is a two-sheeted cover. And if you compactify it by looking over the entire Riemann sphere, it's a two-sheeted cover branched at 4 points. Okay? So if I have a two-sheeted cover of the plane branched at 4 points, then I can think of that. One way to visualize that is to sort of draw arcs joining those points in pairs and then open up those arcs. So we can think of the plane minus those arcs as the plane minus with 2 holes removed. Now, if we take the two-sheeted cover of the plane branched at those original 4 points, what we get are 2 copies of the plane with these 2 holes removed, but with now the boundaries of those holes identified with one another. And if you think about what that looks like topologically, that's a torus. Okay? And that, when, at that point, that began to explain why they could not explicitly evaluate this integral. If you think about it, if we have an integral on a sphere of, say, a holomorphic differential, the integral does not depend on the path of integration. And more generally, since of course there are no global holomorphic differentials on the Riemann sphere, with a meromorphic function, with a meromorphic differential, the integral will just be given as a sum of residues. But if we have an integral of a differential on a torus, now we're in a very different situation. Now the integral depends not just on the choice of starting point and ending point, but it depends on the choice of a path of integration. And so, in fact, what that means is that the integral is only well defined after you specify a path, and the path depends, any 2 paths differ by an element of the fundamental group, which is Z cross Z. What that means in effect is that if you look at the inverse function to the indefinite integral here, that's going to be a doubly periodic function in the complex plane. And they knew at that time that there were no elementary functions in the complex variable that were doubly periodic. They had to invent them before they could express the values of this integral. That's what happened. Weierstrass, for example, introduced the Weierstrass P function. It was the first doubly periodic function anybody had seen. And in fact, you can express these indefinite integrals in terms of the inverse of the Weierstrass P function. So that cleared up a lot of the confusion surrounding these elliptic integrals. And it also gave rise, it sort of kickstarted the whole subject of algebraic curves. The point is that what you see for the first time, you see that you cannot apply the technique we did in the case of a quadratic irrationality, where we gave a rational parameterization of the curve or Riemann surface, W squared equals Z squared plus 1, and we converted the whole integral to integral of a rational function. That can't work here because there is no rational parameterization. And this was the first time that people had actually seen that, in fact, there were curves, there were algebraic curves that were not rational. This led to the introduction of the notion of genus, which had appeared before, but not in the context of the topology of the zero locus of the polynomial equations. And that led in turn to the development of the theory of algebraic curves, which really took off in the second half of the 19th century. So there is my first example of the ways in which the issue of rationality, and specifically the rationality of a cubic hypersurface, turned out to be absolutely central to the development of algebraic geometry. All right. Now, here, I want to move on to the case of surfaces. And again, I want to look at cubic surfaces. And the study of cubic surfaces, well, let me just start by describing the basic result here. And again, I'm sure most of you are familiar with this, but let me say it anyway in a form what I would suggest is, we ask, can we solve a cubic polynomial in 3 variables? And the answer in this case is yes. So the next step is dimension 2, a cubic surface, and I should specify here a smooth cubic surface, S inside 3 space, and I might as well make it projective 3 space, is rational. And let me just explain how that construction goes, and then I'll talk a little bit about the significance of this. The basic idea is, and there are many ways to do this, but the one I think that is simplest, if you start by looking for lines on the cubic surface, and in fact you find, or you show, that there exist on the cubic surface 2 skew lines, L and M contained in S. And then what we get is a birational map from the product of L with M to S. And going left to right, this simply takes a pair of points, P and Q. That's a point P on L and a point Q on M, and it sends it to the 3rd point of intersection of the line PQ with S. I mean, after all, a line in the surface that it's not contained in the surface meets the surface at 3 points. If I take 2 points, one on L and one on M, and draw the line joining them, I've already accounted for 2 of the 3 points of intersection. I can send that pair of points P and Q to the 3rd point of intersection. And going the other direction, if I start with a point R in S, I can map that to the unique line of the form PQ, again with P and L and Q and M, that contains the point R. So this gives me a birational map, okay? It is not, and this illustrates, by the way, one of the points I was making before, this does not give us a one-to-one correspondence between points on S, or solutions of that cubic polynomial, and pairs of points P and Q on P1. For example, the lines L and M themselves on S don't have anywhere to go here. And at the same time, well, I'll just say that. So this is the first case where we have a birational map, but it's not biregular, okay? And this was a huge development because in dealing with curves, right? The basic fact about curves is that for smooth projective curves, a regular map is the same as a rational map, and a birational map is the same as a biregular map. And people in the latter 19th century, when they were dealing with curves, they got a little bit lazy. They didn't think what do we mean by a curve and what do we mean by a point on the curve. They basically said that a curve is a birational isomorphism class. A curve is specified purely and simply by its function field. And the points of the curve can be viewed as valuations on that field. Or another way to say it is, in the latter 19th century, a curve was essentially defined to be an irreducible polynomial in two variables, f of x, y, with the equivalence relation that two curves were the same if there was a birational substitution of variables that carried one into the other. So what was happening in the case of surfaces is that now biregular isomorphism and birational isomorphism diverge. And correspondingly, you have to treat these two types of morphisms separately. And the whole subject of algebraic surfaces is built up on an understanding of just that fact. And things like blow-up maps that didn't exist in the case of curves are now very much part of the geometry of algebraic surfaces. So that was the situation with surfaces. And now, before we go on to threefolds, I want to just point out that there's another question, okay? Again, dealing with rationality. One thing that was observed way back in the 19th century about rationality for curves is that, well, I'll just say it, Larose Theorem says basically that if C is an algebraic curve and there exists a dominant map from P1 onto C, so that's a dominant map from a rational curve onto C, then C itself is rational. C itself is isomorphic to P1. And in fact, in the case of surfaces, the analogous theorem was proven by Castelnuovo and Enriquez. And they proved that, again, the same thing for surfaces. If S is an algebraic surface, then to say that there exists a dominant rational map from P2 to S, that implies that, again, S is rational. So we have these theorems in dimension 1 and 2 that say that being unirational implies being rational. And naturally enough, there was a question of whether the same thing would hold true in higher dimensions as well. And people tried to prove it, but for, again, a long time, people were unable to establish one way or the other whether this statement was true in higher dimensions. And this question was finally answered a good bit later in the 1970s by an investigation of, in fact, cubic threefolds, okay? So here, dimension 3, I want to consider X a smooth cubic hypersurface in P4, smooth cubic threefold. Okay. And what was known for some time since the turn of the century was that X, such an X, is unirational. And that's easy to see, again, by sort of this kind of geometric construction that we use to prove rationality in the first two cases. Basically, what we do is, the idea of the proof here is we fix a line, L in X, okay? And then we consider we consider the set of pairs, P and Q, where P is a point of L and Q can be a priori any point on X, okay? And the condition here is that Q lie in the projective tangent plane to X at the point P. So basically, we're looking at this line sitting inside X, okay? And we're looking at every point of L. We have the tangent plane to X at that point, okay? So this is my point P. This I'm going to be drawing as, this is going to be the tangent plane at P to X. And if I think about what those planes are doing as I move up and down the line L, right, they sweep out. I mean, these are hyperplanes in P4. They're all hyperplanes that contain the line L, and they form a degree 2 family of such hyperplanes. In other words, if we think of the dual projectors, in the dual projector space, of the space of hyperplanes containing the line L, that's a P2, and the tangent planes to X along the line form a conic in that P2, okay? What that means is that a general point in P4 will lie on 2 such hyperplanes, okay? So to say it another way, let's look at the set of pairs P and a line L. This is lowercase l, sorry about that, such that P is in the line L, and L, little l, is a line contained in the tangent plane to X at P and containing the point P, okay? This, what I claim is, this maps, first of all, maps down to L itself, which is a copy of P1. And the fibers here, if you think about it, if I fix the point P and look at the tangent plane to X at the point P, the set of lines in that plane that pass through the point P, the fibers of this map, in other words, are isomorphic to P2. So this space of pairs, a point on L and a tangent line to X through that point, that's rational. That's a P2 bundle over P1. And at the same time, it projects down to X via the map that sends a given pair PL to the other point, again, of intersection of L with X. Again, L is by construction, little l, is a line tangent to the cubic threefold. And it has therefore one other point of intersection with the cubic threefold. We'll map it to that point in X. And by what I said before about the family of hyperplanes to X at points of L sweeping out projector space P4 twice, this map has degree 2. It's generically 2 to 1. So we don't get a birational parameterization of the cubic threefold, we get a unirational parameterization. We get a dominant rational map from this rational variety on to X. That's degree 2 though, not degree 1. So this was sort of, in some sense, the first example that people ran up against where they were able to prove that a variety was unirational but could not determine whether or not it was rational. And things basically stayed in that state of affairs for quite some time. I mean, I think this was an outstanding question as far back as the turn of the 19th to 20th century, and it wasn't resolved. This was solved in the 1970s by Clemens and Griffiths. And around the same time, a number of other people did this as well, Manin and Mumford, and the techniques were all a little different, but I want to talk about the Clemens-Griffiths approach. And the key element that was introduced in this problem, in studying the cubic threefold via, the way Clemens and Griffiths did it, was that it introduced finally the subject of Hodge theory. So Hodge theory was something that had been developed by, well, I guess you'd have to say Griffiths to start with, and then taken up by Deligne and others, but it hadn't really had an application until this. And this was really, so to speak, its coming out party. They really, this was a proof that Hodge theory could be used to establish, to settle questions, open problems in classical algebraic geometry. So the basic idea here is very straightforward. The basic fact to begin with is, but the basic fact that Clemens and Griffiths used is that a rational map can always be factored into blow-ups and blow-downs, okay? So if you want to apply Hodge theory to a problem in birational geometry, it's natural to ask, what does blowing up or blowing down do to the Hodge theory of a variety? Okay. And the answer was basically that when you blow up a point on a variety, on a smooth threefold, for example, you don't really introduce any non-trivial elements into the Hodge theory. But if you blow up a curve on a smooth threefold, the effect of that blow-up map is to introduce, as a direct summand in the weight 3 Hodge structure of the threefold, a copy of the Jacobian, or the Hodge structure of weight 1, on the curve you blew up. So in other words, in particular, if a threefold is rational, what Clemens and Griffiths deduced from this is, if a threefold is rational, its Hodge structure in weight 3, the middle Hodge structure, would have to be a direct sum of Hodge structures of curves. Okay? So the basic idea here is to say that X, our cubic threefold, is rational. That says that the Hodge structure of X is a direct sum of Hodge structures of curves CI. And now what makes this something they can work with is because the Hodge structure of a curve has a geometric construction. Well, not the Hodge structure, you can't construct the Hodge structure geometrically, but you can realize the Hodge structure geometrically. You can think of a Hodge structure, in this case, a weight 3 on a cubic threefold, as consisting of the data of a lattice, the integral homology in dimension 3, or cohomology in dimension 3, together with a decomposition of its complexification into 2 complex conjugate summands. And you can project the lattice into one of those summands and take the quotient to introduce a torus, an abelian variety, as it happens, that somehow conveys the Hodge structure of the threefold. This is called the intermediate Jacobian. And what Clemens and Griffiths were saying is that the threefold is only rational, can only be rational, if its Hodge structure, if its intermediate Jacobian is a product of Jacobians of curves. Now, when you have a Jacobian, that gives you a geometric object that embodies the Hodge structure. And that's what Clemens and Griffiths really used. Once you have the Jacobian, it's relatively, there are a number of ways of seeing or testing whether or not this could be the Jacobian of a curve. I mean, for example, just to mention one, if you have a curve and you look at its, if you look at an abelian variety in general, a complex torus, and let's say it's principally polarized abelian variety, so it has a theta divisor, you can look at the Gauss map on the theta divisor. If I have a theta divisor in a G-dimensional abelian variety, I can map it to the projective space, PG minus 1, by associating to every point on the theta divisor its tangent hyperplane. And for a general abelian variety, in fact, that map will have degree G factorial. But for an algebraic curve and its theta Jacobian and its theta divisor, the degree of that map will be 2G minus 2 choose G minus 1. So that's just one of the many ways you can look at the Jacobian and test whether it is the Jacobian of a curve. And in fact, Clemens and Griffiths carried this out, and they saw that, that in fact the cubic threefold, so in fact, use this to show that a smooth cubic threefold, is never rational. And so any smooth cubic threefold will represent a counterexample to Larose in dimension 3. It will be unirational, but not rational itself. Okay. I mean, there were other ways of approaching the problem, but this, I think, was really, this had significance not only just for the solution of this particular problem, but more generally for the introduction of Hodge theory into the subject of algebraic geometry. Okay, let's move on. And I want to go now to dimension 4, and this really is very much current research. So much so, by the way, that I screwed up when I was writing the abstract for this talk. I neglected to update it from a previous version, and in fact, it's out of date. So I apologize to all the people who have proven some of the results that I'm about to quote now. But let's move on to dimension 4 and rationality questions. Again, I want to focus, at least to start with, on cubic hypersurfaces. That would be cubic fourfolds in P5, okay? Those are going to be my objects of interest, X and P5. Again, I'm going to say smooth cubic hypersurface. Now, again, as I did last time with the threefolds, I want to pose a problem to start with. And this is the one that really sort of attracted our interest from the beginning. See, one thing, if you look at the cases we've talked about so far, cubic curves, cubic surfaces, cubic threefolds, we asked in each case the question, is this variety rational? And the answer in each case was an absolute yes or no, not it depends. So, for example, when we talked about cubic curves, a smooth cubic curve is never rational. It's always a torus, not a sphere. A smooth cubic surface is always rational. It always contains those two skew lines, and that gives us a birational parameterization. And for smooth threefolds, Griffiths and Clemens together proved that a smooth cubic threefold is never rational. So the question you might ask is, leaving aside the question of whether they're rational or not, is the same phenomena going to hold in higher dimensions? Will it be the case that all smooth cubic hypersurfaces of a given dimension are rational, or none of them are? And more generally, you could ask this question about the condition of rationality in general. So let me phrase the question, and then we'll go on to tell you what's been done to answer. So we asked the question, okay, given of smooth projective family of varieties, okay? So that means a family of varieties, X over some base B, and over a given point in B will denote the fiber by X sub B, okay? And again, we're assuming that the morphism is smooth and projective. So the fibers are all projective varieties, smooth projective varieties of a given dimension. And the question is now, if I look at the locus, say set B rational, to be the set of B in B such that the fiber over that point is rational. The question we're going to ask is B rational open in general? Is it closed in general? So in the cases that we've looked at so far, the cubic curves, cubic surfaces, cubic threefolds, the answer to both of these questions is yes. It's an open condition and a closed condition. And that's why, of course, the space of cubic curves or cubic surfaces or cubic threefolds, the answer is always yes or no. Okay. This was the situation back in the 90s, I guess it was, when Brendan Hassett first undertook to think about this, okay? And Brendan Hassett did not solve the problem at that time. He set up a system whereby he made it plausible that the answer to both of these questions in higher dimensions is in fact no, despite the fact that for the first three cases that we've seen, the answer is yes to both. And the way he did this, okay, so this is going to be, I'm going to describe first of all Hassett's work, and then I'm going to describe more recent work of his and others. He proposed to, again, look at the Hodge structure. Of X, where again, X is our cubic fourfold, okay? Now, it's not hard to write down, in fact, quite a bit is known. Voisin, Denagi, Beauville, many people had thought about the Hodge structure, excuse me, of a cubic fourfold, and in fact had proved theorems about it, like a Torelli theorem and even a surjectivity of Torelli. And the Hodge conjecture was proved for cubic fourfold. So there's quite a bit that we knew about the Hodge structure. In particular, the Hodge structure of X has dimensions 1, 21, and 1. Now, the same principle applies, okay, as in the case of threefolds. The same principle that Clemens and Griffiths used, which is to say that if a fourfold is rational, right, then it can be built up from P4 by a series of blow-ups and blow-downs. And the effect of a blow-up is, again, to introduce as an extra direct sum-end to the Hodge structure of the locus you blew up. So if you're looking specifically at the middle dimensional Hodge structure, which is the only non-trivial one for a cubic fourfold, if you blow up a point or a curve, it doesn't affect the middle Hodge structure. If you blow up a surface, you introduce a copy of the middle Hodge structure of that surface as a direct sum-end of the middle Hodge structure of the fourfold. So in other words, in order, if the cubic threefold is going to be rational, its Hodge structure, which again has dimensions 1, 21, and 1, has to be built up out of Hodge structures of surfaces. Now, that's not 100% if and only if, because again, we can blow up and we can blow down. And blowing down can remove if a Hodge structure is not irreducible, then blowing down can eliminate a sum-end of that Hodge structure. That didn't happen when we were just blowing up curves, because the Hodge structure of a curve is irreducible. But here, this became more of an issue. So the question nonetheless is, does this look like the Hodge structure of any surfaces that you know? And the answer there is a clear yes. This looks like the Hodge structure of a K3. But it's not the Hodge structure of a K3. The Hodge structure of a K3, so again, this looks like the Hodge structure of a K3 surface, except the Hodge structure of a K3 surface has dimensions 1, 20, and 1. And that doesn't quite jibe with this because, again, given the surjectivity of Torelli, what's true is that the Hodge structure of a generic cubic fourfold, general cubic fourfold, is irreducible. So it cannot relate to the Hodge structure of a K3 surface. That ultimately led Hassett to ask, what about those cubic fourfolds whose Hodge structure is not irreducible? And in particular, if you look at cubic fourfolds, well, in general, in the middle dimensional cohomology, there's one class, which is the square of the hyperplane class, okay? And it's really the orthogonal complement of that we're interested in. That does have the right numbers as the K3, but it has the wrong signature. So again, you're not going to relate it to a K3 that way. But, Hassett said, what if we looked at a cubic fourfold that had a second algebraic cohomology class? Okay, look at cubic fourfolds with a second algebraic cohomology class. So in addition, let's call that gamma, and that's in addition to the hyperplane class squared. Okay, now what Hassett found was you could look at the orthogonal complement of the rank 2 lattice spanned by gamma and omega squared. Okay, the orthogonal complement of the span of those two is a Hodge structure with dimensions 1, 19, and 1, and this could be the Hodge structure of a polarized K3. And in fact, Brendan went on to find a series of examples, accountably many, loci in the space of cubic fourfolds of those that contained a second algebraic cohomology class and such that the orthogonal complement of the span of those two classes was the Hodge structure of a K3 surface, of a polarized K3 surface. So this was the picture that Hassett built up. He says, basically, you look inside the space of cubic fourfolds. That's parameterized by a big projective space, or the quotient of a big projective space by PGL 6, I guess it would be. And he says, in there's a countable collection of divisors in that moduli space corresponding to cubic fourfolds that have a second algebraic cohomology class. There's cubic fourfolds that contain a two-plane, cubic fourfolds that contain a quadric surface, cubic fourfolds that contain a cubic scroll in P4, cubic fourfolds that contain a rational normal scroll or a Veronese surface. All of these give rise to divisors in the moduli space of Hodge structures, and they all correspond to Hodge structures or cubic fourfolds of this type. Okay? Now, what the point is that if we have a cubic fourfold that lies outside this countable union of divisors, it does not appear to be rational. We don't know that yet, but it does not appear that a general cubic fourfold is rational at this point. And on the other hand, those that do have this second algebraic cohomology class, and specifically those for which the orthogonal complement of the rank 2 lattice they span is the Hodge structure of a K3, of a polarized K3, those are potentially rational. And in fact, there are some examples of cubic fourfolds that are known to be rational, and they all fall into this category. They all are of this type. So the picture, okay, the picture that we come up with is that in the space of cubic fourfolds, so this is called this M, is the space of all cubic fourfolds. Again, there's a countable union of divisors in that space corresponding to cubic fourfolds that we can call, say, potentially rational. Those are the ones that have the second algebraic cohomology class and whose primitive Hodge structure, so to speak, is the Hodge structure of a K3. And what the suggestion is that among cubic fourfolds, the ones that are rational should be or may be just the union of this countable collection of divisors. Meaning, in particular, that it's neither open nor closed. So the guess here is the locus of rational fourfolds, cubic fourfolds, is a union of countably many divisors in the space M. And this is, again, a countable union. So that would answer our naive question, is rationality an open condition or a closed condition? That would answer it in the negative for the most part. Okay. Now, unfortunately, this is as far as Hassett got in his thesis. He sort of introduced this picture, which became, in some sense, the way people thought about the problem for a couple decades after, but he wasn't able to answer the problem. And a large part of that, and this is one of the reasons I wanted to mention this, is a large part of that is that unlike the case of the Hodge structure of a cubic threefold, where there was a geometric object, a Jacobian, associated to the Hodge structure, and you could sort of carry out geometric operations like taking Gauss maps on the theta divisor in that Jacobian. There's nothing analogous to that here. And this has been one of the biggest frustrations for those of us who deal with Hodge theory in any way, shape, or form, going back to Griffiths, that there isn't in general a geometric object you can associate a Hodge structure to. Sorry. That you can associate to a given Hodge structure. So again, the one exception is the case of Hodge structures of weight 1, where you have a Jacobian. In higher weight, there doesn't seem to be a useful geometric object that you can attach. And in particular, that sort of Hassett's approach got stuck here, okay? Well, but at the same time, I think people were motivated by this picture to look more closely at this question of how rationality behaves in families. And in particular, people like Voisin introduced some new techniques that were ultimately that allowed Hassett, Tschinkel, Pirutka, Kontsevich, and others to actually answer the questions that had been originally asked. We still don't have a complete answer for cubic fourfolds. That's still a little bit beyond us, but in fact, what we can say is two things. First is we have Hassett, Pirutka, and Tschinkel, who prove a big theorem that says that there exist moduli of fourfolds. And again, these are not going to be the cubic fourfolds. Cubic fourfolds gave rise to the picture, but this is a different family. This is going to be quadric bundles over P2. So imagine that you had a P3 bundle over P2, and inside that P3 bundle, you had a family of quadric surfaces. Those quadric surfaces would form a fourfold. And again, you can ask about the rationality of that. There exist examples of such moduli where the locus of rational varieties is neither open nor closed. Okay, so that settled that question. And again, it didn't come directly from cubic fourfolds, but it came fairly indirectly from cubic fourfolds. And there is, moreover, it gave rise to some further work of Kontsevich and Tschinkel, which says that, in fact, this is not just a made-up example. This is the general picture. In other words, given any family, smooth projective morphism, X over M, as we had before, given any smooth projective family, oh, sorry, we had a B before, I apologize. Any smooth projective morphism like this, then the locus of rational points in base B, where the fiber is rational, is going to be, in fact, a countable union of subvarieties of B. Again, that includes the possibility that everything is rational or that nothing is rational. But in general, what Kontsevich and Tschinkel prove is that, in fact, this is the general picture. You get the locus of rational varieties is a countable union of subvarieties, which is really, to me, it's a huge deal, because what it suggests is that, in contrast to the case of dimensions 1 and 2, where rationality is a geometric property of a variety, it's saying that in some sense, rationality in higher dimensions is an arithmetic property rather than a geometric one. There is one positive statement that we can get from this, even though it's true that B rational is not an open subvariety of B or a closed subvariety of B. What is true is that rationality behaves well under specialization. If I have a family of varieties and they're all, again, in the smooth projective setting, and they're all rational except for one, that one is going to be rational as well. In other words, we can specialize. When we specialize a family of rational varieties, the specialization, assuming it's smooth again, is rational. So that's where we are, at least for now, until someone thinks to ask their question about cubic fivefolds or cubic sixfolds. And there are a lot of questions out there about higher dimensional, but I think I've spoken more than the hour I had intended to speak, and I think I've made the case that cubic hypersurfaces seem to be a generator of a lot of algebraic geometry. So I will stop there. Thank you for listening.
Good, that's a beautiful talk, Joe. So let's see who have questions. Can you see it? Ryan, maybe you can.
I'm not seeing hands.
If people have questions, raise your hand. It's one of the options at the bottom of your screen.
Okay. We have, Francois Greer. How you doing?
Well, let me ask you, besides Hodge structure, are there other really powerful tools?
I don't know of any in general. I should have mentioned this. Mumford, for example, when he was doing the cubic threefold, he did it a different way, and he did it by observing that torsion in H3, in the third homology, or cohomology, I forget which, is a birational invariant. And he was able to use that fact to, I think, prove that the cubic threefold was not rational. Or maybe it was another example that he applied that to. But in any case, there have been other techniques that have been applied to these questions, and I don't think that any of them has a consistent track record of success, though.
Hi, Joe. Could I just ask?
Yeah.
You said that in dimension 1 and 2, rationality is sort of a geometric property, and in higher dimensions, it's an arithmetic property because you have this countable phenomenon. Do you know what the answer is for smooth threefolds in general? Or do you have an expectation for whether...
I don't know what the answer is for threefolds. That's an open... I mean, I think... oh, wait, I should look this up. I'm not sure if Tschinkel applies to threefolds or not, but let me say it this way. I'm reasonably confident of this. There aren't any known examples of families of threefolds for which the locus of rational members of the family is not open or closed.
Let's see.
All right. See, I have a question from Jenya Zaitman.
Yeah.
Oh, here we go.
Can you hear me?
Yes, I can.
Okay. Let's see. What happens in non-zero characteristic?
You'll have to ask someone else about that. I really don't know what the situation is.
I've heard you can get all kinds of weird things can be unirational in non-zero characteristic, but
yeah, no, I really, that's something I really am just ignorant. I don't know. You do have to be, of course, another thing in characteristic P is you have to ask the question. There are different flavors of the question. You can ask for varieties that are stably rational or unirational, and as opposed to just simply rational or unirational. And those are two different questions. So I don't know much about that. I apologize.
How does unirationality play out in this picture?
Well, that's something that has not been much addressed, whether unirationality is I don't know of any examples where unirationality is not open or closed.
But for cubic hypersurfaces, how does it work?
Oh, sorry, the cubic hypersurfaces are all unirational. Essentially the same construction I showed you works in any dimension. You just choose a line on the cubic hypersurface. You look at the tangent hyperplanes to the cubic hypersurface at points of that line, and they will, in the same way, they will give you a two-sheeted map, a degree 2 cover of the cubic hypersurface by a rational variety.
I see. Okay, thanks.
So, let's see, what else was I going to say? Yeah. If you don't mind my going a little bit off topic here, there's a further condition that people have introduced that, in some sense, you could make a case represents the right generalization to higher dimensions of the notion of rationality in dimensions 1 and 2. And this is the notion of rational connectivity, which was introduced by Campana, Kolar, Mioka, and Mori. And the idea is you say a variety is rationally connected if you can join two general points by a chain of rational curves. There are many, many equivalent formulations. And this is a property that coincides. It agrees with rationality in dimensions 1 and 2. But in higher dimensions, it behaves very differently. And in some ways, you have to say, it behaves much better, in the sense that rational connectivity is an open condition. It is a closed condition. We know for any hypersurface exactly, any smooth hypersurface, excuse me, we know exactly when they're rationally connected or not. So there's a further issue here, which is how does rational connectivity relate to either rationality or unirationality? And again, we don't know, in the latter case especially, we don't know whether or not unirationality coincides with rational connectivity, which is crazy because it can't, it shouldn't, but we have no counterexamples. Anyway, I just want to throw that in.
I have another question about these divisors. Are these Kudla-Nielsen divisors, and are they all of them, or is there an additional condition on them?
There is an additional condition. What Hassett finds is he has a very simply indexed sequence of these divisors. Basically, what he says is, suppose you look at a cubic fourfold that has one of these, a second algebraic cohomology class, and you look at the sublattice of cohomology spanned by omega squared and gamma. You associate to that the discriminant of that lattice with respect to the intersection pairing. And what he proves is that there is, for every discriminant congruent to 0 or 2 mod 6, there is a divisor, an irreducible divisor in the moduli space of cubic fourfolds that have such a lattice in their algebraic cohomology. So he has a neatly indexed series of divisors. And then he finds a countable subsequence of this divisor, where when you take the orthogonal complement of this rank 2 lattice, you get the Hodge structure of a polarized K3. So it's that subsequence of divisors that are the sort of logical candidates for rational cubic fourfolds. All right. Well,
so what happens to cortex?
So what about stable rationality? How does that fit into these families?
You got to talk to a grown-up about that. I have not been. I mean, there's a lot of results about stable rationality going back to Beauville, even before this sort of work of Hassett, Voisin, and those, and Tschinkel and everybody. You know, this was a problem that that Beauville and others were thinking about, is stably rational. Stably rational, by the way, means that if you take a product of your variety with some projective space, that's rational. That does not imply rationality, and there are examples of varieties that are stably rational but not rational. But to be honest, I'm not an expert in that area, so I wouldn't try to relate it to what I've been talking about.
There's also a question in the Q&A.
Ah, okay. Let's see, I'm not seeing. Okay, well, go ahead.
The question is, what do you mean by arithmetic or not geometric property?
Pardon me?
The question is from anonymous attendee. The question is, what do you mean by arithmetic, but not geometric property?
Yeah, no, that's you know, it's more of a feeling than a technical definition. The idea is that most geometric conditions on varieties that you can impose, they tend to be closed conditions or open conditions. And it's strange, if you think about it, to find a condition that you could impose on a variety that behaves this way, where you can have where the condition is neither open nor closed, but you have a countable union of subvarieties where it holds. So that was really just sort of an expression of the thought that, maybe if you're doing algebraic geometry in higher dimensions, the condition of rational connectivity is the more suitable generalization of the notion of rationality.
So Joe, what happens to hypersurface with degree less than n+1 in general?
Well, there again, we don't know. If we have a Fano
hypersurface with degree less than n+1.
Right.
Yeah.
So that's what I call a Fano hypersurface, because it has negative canonical bundle. It's a Fano variety. Now, it's known that those are all rationally connected. They have tons of rational curves. It's not known whether any of them are rational. I mean, beyond the obvious low degree cases. It's not known whether they're rational. It's not known, in fact, whether they're unirational. And it is strongly suspected that they are not unirational. Since you asked the question, let me put in a plug for this. To say that a variety is rationally connected means that it has lots and lots of rational curves. The original condition says simply that you can join 2 points with a rational curve, but that implies, in turn, if the variety is smooth and projective, that implies that there are rational curves through any finite collection of points. So there's a lot of rational curves, but the condition of rational connectivity does not imply the existence of so much as a single rational surface on your variety. You could have a rational a rationally connected threefold that has no rational surfaces on it, whereas, of course, rational connectivity, being unirational implies that you have rational subvarieties of every dimension less than the maximum. So in fact, there's a whole series of conditions that you could possibly interpolate between rational connectivity and rationality. You could require that there be rational curves, rational surfaces, rational threefolds inside your variety, and this forms potentially a sequence of conditions. But again, we don't know that those aren't all equivalent conditions. Now, if you look at hypersurfaces in the Fano range, as you said, like hypersurfaces of degree n in Pn, right? If you do a naive dimension count, what you see is that you don't expect that to contain any rational surfaces. So that should be an example of a variety that's rationally connected, but is not unirational. But no one's been able to prove that. That's what I'd like to know. I'd like to know that a general hypersurface of degree n in Pn does not contain rational surfaces. And again, that's excluding the case of n equals 3 or probably 4 as well. Okay, sorry about the length of that.
Okay, any other questions?
Is the property of being unirational geometric or arithmetic?
Yeah, I really don't know. I really am kind of at a loss.
Okay, other questions? Okay, if there's no questions, let's thank Joe for this beautiful lecture, and I hope you write it up soon and we can post it in our web. So next lecture will be at 3 p.m. Simon Donaldson will talk about instantons, Young Mills. So I hope you all come back. So let's have a plot for Joe.
All right. Thank you.
Okay, see you later at 3 p.m. Thank you.
Okay.
Just a note to the audience to attend the next lecture at 3. You can use the same email link that you received before. You'll probably have gotten another reminder for it by now if you've registered.
Okay, thank you.
All right, Ryan, thank you. Yao, thank you. Yang, thank you. And
Thanks, Joe.
I'm going to peel
Thank
off
you.
now, I guess. I'll see you.